So osmosis is the flow of solvent from a solution of lower solute concentration to one of higher solute concentration. So this has to do with the tendency, nature's tendency to mix. Okay, so let's look at this. I have a tube. It looks like a U-tube, right? It's a tube that's shaped like a U. Okay, it's a glass tube. There's a semi-permeable membrane, which means some things can go through it and some things cannot go through it. So you have the solute and water. So obviously we have pure water over here and a mixture. Well, there's going to be a net migration of water to the solute particle, right, the mixture, so that what happens here is this is a pressure, right? So this weight, this water right here, that mass, that gives us a pressure, right? Right, because this water's holding that up, and there's a net effect of pressure there. If you remember how a barometer works, okay, this mass of water is directly it's related to the pressure. URE. It's related to the pressure holding the water up. So this happens because nature wants to even out the concentration of the solute. And so water is going to go over. Now, reverse osmosis is when you would put, let's say, a piston here, right, and push this water through, and then you have the solute left and all the pure water out. Actually, a very good way to purify water. And in fact, a lot of places, I believe, a lot of ships and stuff still use reverse osmosis to get seawater into fresh water when they're at sea, because water is very heavy, right? It's 8 pounds a gallon, and we use a lot of water. So, and this is why we can't drink ocean water, right? You drink salt water, you have a higher concentration of solute in your stomach than in your cells, and so water goes from your cells into your stomach, and it dehydrates you more, right? When we drink fresh water, water goes into our stomach and goes into our cells, because our cells are more concentrated with solutes than fresh water, and so that's why we drink water. It's good for us. Okay, so now pressure. That pressure is capital P. I'll use green, but it's the Greek letter P, pi, equals I, the Van Half factor, M, the molarity, gas constant, and the temperature. All right, so let's look at this. So this is osmotic pressure. In atmospheres, I, of course, is the Van Hoff factor. Molarity, and temperature. So that means the R we have to use is still the gas constant. All right, but which one? Well, I have atmospheres, liters, moles, and Kelvin. So it's going to be 0.08206 liters, atmospheres, moles, Kelvin. All right, those are our units. Right. So this is all osmosis is. Osmosis is going when you have a semi-permeable membrane, like a filter, but it's not paper. And you have water, a net migration of water. In this case, the net migration of water will go left to dilute the solution. All right, let's try about number 81 here. Oh, no, 81 is not. How about this example? We'll go back to 81 in a minute. This example. Calculate the osmotic pressure of a solution of 24.6 grams of glycerin in 250 milliliters of water at 298 Kelvin. So we're calculating the osmotic pressure. So that's pi equals IMRT. Hydrocarbon, right? Oxygen, well, not hydrocarbon. C3H8O3. So it's a molecule. I is 1. Okay, so pi equals I, which is 1. Molarity, I have 2, well, we don't know the molarity yet. Okay, we have 24.6 grams of C3H8O3 all over 250 milliliters. Well, we do 12 times 3 plus 8 plus 16 times 3. We get 92.11 grams of C3H8O3 is 1 mole of C3H8O3. And then, of course, 1,000 milliliters, 1 liter. We get a molarity. It looks like it's 1.068 molar C3H8O3. Great. Now we can do this. So pi equals 1 times 1.068 moles per liter. 0.08206 liters, atmospheres, moles, Kelvin, and 298 Kelvin. So that means pi would be 26.1 atmospheres. That sounds big. Sometimes these osmotic pressures can be quite large. Quite large. Okay. All right. One more of these. A solution containing 27.55 milligrams of an unknown protein per 250 milliliters of solution was found to have an osmotic pressure of 3.22 torr at 25 degrees Celsius. What's the molar mass of the protein? Okay, well, let's look at that. I have pi equals I M R T. Okay, do I have T? Check. 25 degrees C, which is 298 K, right? Or 298.15 or whatever you want to use. All right, pressure here, 3.220 torr. Protein, I is 1. R, of course, is R. We always have R. So we're kind of looking for the molarity here, aren't we? All right. So units, of course, 298 is good. R is going to be good. M, we're going to get M. Pi, the pressure. What is... Can I use torr? I don't think so. What do I have to do here? Well, we have to take our 3.220 torr, and we know that 1 atmosphere is 760 torr. So that becomes 0.00424 atmosphere. All right. Now I think we can solve for M. So 0.00424 atmospheres equals 1 times M times 0.08206 206 liters, atmospheres, moles, Kelvin, and 298K. So M turns out to be what? Well, it looks like it's going to be 1.73 times 10 to negative 4 moles per liter. Alright, so what do we know here? That's the molarity of the protein. That doesn't help me. I need molar mass, right? So I need grams of protein over moles of protein. Do I have the grams of protein? Right there. I got grams. Moles. Well, I know my moles per liter. Don't we have a volume? I have 25 milliliters. So if I start with 25.00 milliliters, and we know that 1,000 milliliters is 1 liter, and in 1 liter I have 1.73 times 10 to negative 4 moles of protein. Wouldn't that give me approximately 4.33 times 10 to negative 6 moles of protein? So the molar mass then is just grams per mole. It's grams of protein over mole. Well, my grams, I have 27.55 milligrams, right? So that's times 10 to negative third grams. And my moles was 4.33 times 10 to negative 6 moles. That should give me my molar mass. And it's 6360 grams per mole. I mean, these proteins can be quite large, like 60,000, 6,000, 60,000, 50,000. That's not a bad number. So, and that's about as complicated as osmosis can get for us. I is 1. I guess we could throw out I being not 1 and make it just a small amount more complicated. But that's it.